Okay, so last time we were talking about the efficiency gap. That is sort of a statistical way of measuring how fair the districts are in terms of packing. The efficiency gap measures packing. I wanted to just do one more example of that. You're going to have plenty to try on the homework. By the way, I printed out the homework again because the homework again this week has some pictures to draw on, so I'll hand those out at the end. The efficiency gap this is actually the standard measure of gerrymandering packing, and the efficiency gap has been used in several high-profile court cases by people trying to prove that this or that map is fair or unfair. If the efficiency gap is too high, that would indicate some kind of unfairness. I thought we would look at just a specific real-world example. This is the state of Connecticut U.S. House Representatives in 2020, the last election. You know, we're having another election in a couple weeks, which will decide these 5 districts again. But as of now, since 2020, the 5 districts are all represented by Democrats. I looked up the numbers for the election, which happened in 2020. You know, for most of these things, we've been looking at the pictures, but actually the picture is not really relevant with the efficiency gap. All you have to know is how many votes each side got, and then you figure out the wasted votes and all that. You don't need to look at the picture for that. So I'm just going to tell you the numbers. We have 5 districts in the state of Connecticut. 1, 2, 3, 4, 5, right? And I'm just taking votes for Democrats and Republicans. There are sort of third-party candidates in these elections also, but I got rid of those. So only looking at Democrats and Republicans here. And I will tell you, these are in thousands. I rounded everything to thousands, just so that we don't have to have a whole bunch of digits. So anyway, in District 1, the D's got 223,000 and the R's got 122,000. All right. These, on a typical homework or test question, I just have to give you all the numbers and then you do the rest. So I will tell you, in District 2, the D's got 218, the R's got 140. In District 3, it was 203 to 138. In District 4, it was 224 to 131. And in District 5, it was 192 to 152. All right? So you can see the D's have an edge every time. I suppose District 5 was the closest of all of them. But, Connecticut is sort of reliably Democratic state on the whole. Although there are a lot of Republicans in Connecticut. They just never have enough in order to win one of these districts. Okay, so this is the amount of information that somebody just has to tell you, but from here we can find the efficiency gap. That's what I want to do here. Let's find, I guess I didn't say that, find the efficiency gap, right? That's our goal. So we have to make the rest of this chart, and I hope you remember from last time what is important in the chart. The next column that we need to make is the total amount of votes in each district, and this column is just you add up these two numbers each time. So I did these ahead of time. You can use the calculator, of course, on the homeworks. On a test, I probably wouldn't give you sort of big numbers like this just because it's a little annoying to do by hand, but these are the totals. 345 for the first, 358 for the second, and then adding the next two is 341. The next is 355, and the last one is 344. All right, those are the totals per district. You just add the previous two columns together, and that's the total. All right. And actually, eventually you're going to have to add up this whole column, and I did that also with my calculator. I got 1743 for that. That's the total number of voters in the whole state who voted in this election. 1,743,000. All right. Anyone remember what's the next column that we need? Yeah, the threshold in each district. This will be 1/2 of this number, and then you either round it up or you add 1 to get one more than 50%. So in the first, so this is the threshold. Again, you can use your calculator to do this. On a test or something, I would make the numbers a little easier to divide in half. Oh, it's not so hard, is it? So the threshold for the first one is 173. If you divide 345 by 2, you get 172.5. I don't want to deal with 0.5, so I just round up to 173. That's how much you need to win in the first district. Okay, the other ones, do you mind if I just tell you? The next one is 179. The next one is 171. Then 178, and then 172. All right? I hope this isn't such a boring example. I'm just telling you all the numbers, but these are easy to figure out if you have a calculator. All right? Then the interesting part is who is wasting in each of those districts. So I have the D wasted versus the R wasted, and this is really where the good stuff happens in terms of the efficiency gap. This is the important part. So in the first row, I hope you remember the rules for wasted votes. Maybe before I try and figure out the numbers, I will just circle the winners as I usually do. And as we all know, in the state of Connecticut, the D's won every time, and that is likely what's going to happen in 2 weeks when we have these elections again. I don't know much about Connecticut politics, but I don't believe that there are any real contenders on the Republican side. I know I got a bunch of junk in my mail yesterday from Jim Himes, who's the Republican in this district, and so I don't even remember the name of his opponent. I like saying the name of Jim Himes. Anyway, what about the wasteds? Remember, the rule is all votes for the loser count as wasted, and any votes for the winner beyond the threshold count as wasted. So in the first row, I can immediately say the Republicans wasted 122. That's because all votes for the loser are wasted. And then how many votes did the D's waste? Anybody? Can anyone say? All votes for the winner beyond the threshold are wasted. So what would that be here? Yeah, 50. Yeah. That would be the D's got 223. The threshold was 173. How many extra is that? If you have a calculator, you can subtract them, or in your head, it's 50 here. So this right here, D wasted for the first one is 50. They got 50 more than was required, and those are extra votes which are wasted. All right? And you just got to figure this out in each row. So in the second row, again, the Republicans lost, so all the R votes are wasted. That's 140. The D's won with 218. The threshold was 179. So if you're using a calculator, you would do 218 minus 179. You could probably do this in your head if you had to. I did this. I got 38. 218 minus... Is that right? That can't be right. Yeah, it better be 39. Sorry. It's going to mess up the rest of my whole scene here. All right, because you're going to have to add up those columns at the end. Okay, next one. 203 for the D's, 138 for the R's. Again, all the R's are wasted, so the Republicans wasted 138. And then for the D's, it's going to be whatever 203 minus 171 is. On my paper, I said it was 32. Which I think is correct. All right, you just got to subtract the numbers here. The next row, the R's wasted everybody, 131. And then the other one is 224 minus 178, which is 46. We're almost done with this one. And then the last row, the R waste 152. All votes for the loser are wasted. And then the D's waste 192 minus 172 is 20. Even I can do that without a calculator. All right, this is the hard work, such as it is. Now it's just a matter of writing down our final answer. In order to do that, we add up all the wasted votes in all the districts. So if I add up all those R wasteds, I got 683. And if I add up all the D wasted, on my paper it says 186, but I think it's actually 187 because I messed up one of the numbers inside there. All right. And then anybody remember how you write your actual final answer? It's a percentage, a fraction. Yeah.
You subtract D wasted and R wasted, and then the denominator is the total.
Yeah, right. It's the numerator is you subtract these two things. That is the thing on top of the fraction, and it's always the bigger one minus the smaller one. So this is 683 minus 187 divided by 1743, and that's the answer. If you have a calculator, you can do the subtraction and the division and turn it into a percentage. So this, if you do the subtraction, I believe you get 498 on top. Or is it 497? 96. Yeah, I'm off by 1 on my paper. 496 over 1743. And then if you like to turn this into a percentage, this is around 29% if you round it. All right, this is the efficiency gap. And when you say the efficiency gap, it's always some percentage, and then you should also say in favor of somebody. So the efficiency gap is 29% in favor of who's being benefited by this? I would say the D's are being benefited because the R's have more wasted votes, far more, right? So this is 29% in favor of the D's, all right? That's how we would write the answer. Any questions about that? It's just a bunch of numbers. You just there's no real hard step, I suppose. You just have to kind of keep straight what you're doing from one step to the next. All right. Let's talk a little bit about this number. Like in the context of the real world, actually, this example, I wanted to do Connecticut just because that's where we are right now. But Connecticut is not really a great example to do the efficiency gap computation with, because this actually is a super high number. And this in the real world would suggest a seriously gerrymandered map, although that's not really the case in Connecticut. I would say this one is super high in numerical terms. 29% is like alarmingly high in the real world, but it's only that high because it happens to be that in the state of Connecticut, the D's won every time. And so every vote for every Republican was always wasted. I would say this is super high, but all districts are D in this case, in the state of Connecticut. And actually, if you look at the way the state of Connecticut is arranged and the way the lines are drawn, they're not all D's because there was some kind of Republican stronghold which was totally cracked into Democrat districts. That's not actually the case in the state of Connecticut. That has happened, elsewhere in the country. But all the districts in Connecticut happen to be Democratic, and so when you do this, when there's only 5 districts here, you end up getting a fairly high percentage just because every Republican vote is totally wasted. So this is a little it's not unrealistic, the numbers, but in the real world, actually, you wouldn't use the efficiency gap to analyze this situation. So I'm going to say the efficiency gap is statistically meaningful. It's not really statistically meaningful in this example, although you can still do it if you want to. The efficiency gap is statistically meaningful when we have many districts with, I will say, diverse populations. I don't mean diverse as in like ethnically diverse or that kind of thing, but I just mean like many districts in which, the D's are winning some and the R's are winning some other ones, right? Which is not really the case in Connecticut. Connecticut is not so diverse in terms of the districts, in terms of their politics, right? Every district in Connecticut is like a little bit more Democratic than they're Republican. And so the efficiency gap doesn't actually measure the situation very well. So it's the best, this efficiency gap works the best when you have a lot of districts, like more than 5. 5 is not really very many. And those districts individually have diverse opinions. So that the D's are going to win some and the R's are going to win some, and then you can analyze the interplay between who's wasting more on either side. it doesn't really work very well with that state of Connecticut map. So I thought maybe I would tell you, just like from a statistical point of view, a quote-unquote like normal range of a typical map which has not been manipulated is generally regarded as something like 0 to 5%. This is what like people in this business view efficiency gaps of 0 to 5% as sort of typical for a map with no signs of manipulation. This is the range that you would expect. So from that point of view, 29 is way too high. Although, like I said, that's because there's only 5 districts and they all went to the Democrats. A normal range is something like 0 to 5%. I would say these people, the people who are used to evaluating these kinds of maps, generally, like sort of a rule of thumb is that over 7% is a bit of a red flag. It's not proof that people are cheating, but it's, cause for concern if the efficiency gap is above 7%. Last time, if you recall, I showed you a map of the state districts in the state of Wisconsin, which had, just by eyeballing the map, it seems to have some pretty clear evidence of packing and cracking to benefit the Republicans. So that map, this was the 2018, come on now, 2018 Wisconsin state representatives. This one has efficiency gap of 10%, and that was in that year, 2018. That was among the very worst if you looked across all the states and calculated all the efficiency gaps. So 10% is regarded as like super high. And actually, there have been some states which have proposed making it illegal to make a map with efficiency gap higher than 7% or something like that. Although I don't believe there are any laws that actually say that have been passed. People always want some kinds of exceptions. This Wisconsin map favors the Democrats, although there are similar maps, not as many. The Wisconsin favors the Republicans. There are maps elsewhere which are gerrymandered to favor the Democrats, although the Republicans have done this a little bit better. Let me just say the efficiency gap is used in court cases, and like I said, there are people who think that we should use it as the basis of laws to outlaw certain types of maps. Is used in court cases. It has been used to argue in front of the U.S. Supreme Court, and there was a famous case, it might have been this Wisconsin map that went to the Supreme Court, and Chief Justice of the Supreme Court, Roberts, when it was explained, one of the lawyers was arguing this map is unfair because the efficiency gap is too high, and they had to actually explain to, these old folks on the Supreme Court how the efficiency gap works. Like, you got to count up the wasted votes and whatever. And John Roberts, the Chief Justice, called it gobbledygook. He was not impressed. I guess he thought it was too complicated. He was like, man, I'm not trying to hear all that math. Get that out of here. I don't know. I feel like it's not that complicated. I suppose it is kind of complicated if you're the Supreme Court justice and you're not used to that kind of thing. But it is a problem, if you're trying to use these kinds of mathematical measurements in the real world. You got to kind of sugarcoat it a little bit, or else people won't listen to you anymore when you start talking about the math. Story of my life, right? This is all I want to say about the efficiency gap. It is an important thing, and like if you read fairly like decent newspaper articles about gerrymandering, they will often mention the efficiency gap as one way to measure if something is gerrymandered really badly or not. All right. That's all about the efficiency gap. In our remaining 30 minutes or so, we can start to talk about, I got 2 more measurements of gerrymandering, and then that's actually the end of talking about gerrymandering. So 2 more measurements. We'll finish this whole thing by next week, by the end of next week. 2 more These are purely geometric measures. Purely geometric. That is, it has nothing to do with counting up the votes for the D's and the R's or anything like that. It's just looking at the shapes, all right? Geometric measures. These are measurements trying to measure in specific ways how weird the shapes are. Because, as you know, like, if you want to manipulate the maps, the standard way to do that is to make the shapes really weird in order to have some effect that you're looking for. And so rather than counting up all the wasted votes or whatever, you can just look at the shapes. And if the shapes look really weird, that's another sort of red flag that would indicate that maybe the map is being manipulated. So the idea here is something like maybe like that. This is not so weird. As a shape to make a district, that, in my opinion, is not so weird. But something like, you know, this one is very weird, right? And the idea here is you look at the map and with no regard for where the voters are or who's voting for who, you just look at the shapes and say, I want them all to look more or less like this. And if for some reason one of them looks like that, this is a sign that probably somebody is trying to mess with the system and trying to manipulate the election. All right? So that's the idea. Purely geometric. And I have two purely geometric measures of how to measure how weird is the shape. You need specific measurements. You can't just look at it and say, well, yeah, the one on the right is pretty weird, isn't it? I mean, am I right? It's weird, right? You can't just like say it's weird. You have to have some kind of actual way of saying it's. I know how to measure how weird something is. So how weird is it? There are actually two very specific measurements that we're going to talk about. There's more that we're not going to talk about. They have cute names. So the first one is called the convex hull ratio. You can sound really sophisticated when you talk about this. How do you know the one on the left is less weird than the one on the right? It's because the one on the right has a very low convex hull ratio. It does. We will eventually learn how to find the convex hull ratio. And then the second one has an even better name. It's called the isoperimetric quotient. Sounds like you're on Star Trek when you talk about that one. These are just two different ways of analyzing a shape and giving it, actually these are also percentages, and you give it like a score where 100% is like a perfectly nice shape and 0% would be a ridiculous sort of wormy shape like this one over here, all right? So these are going to be specific measurements which give us percentages. So I'll say each one. Actually, these ones, for whatever reason, people generally don't write them as percentages, so each one is just a number, a score, if you will, from 0 to 1, like some number in between 0 and 1, which, of course, you could think of as a percentage if you want to, but it'll be like, you know, the convex hull ratio of this shape is 0.8 or something like that, which means it's sort of like 80% good. So in these examples, 1 is the best. By best, I mean not weird. And then 0 would be the worst, which I mean super, super weird. All right, this is what we are aiming to talk about. Okay, let's talk about the first one, is the convex hull ratio. So the convex hull ratio. This is the first one. The other one is the isoperimetric quotient, which we'll talk about next time. The convex hull ratio. This is about convex shapes. So we got to talk about shapes. So here's some like basic geometry. I say basic not because everybody should know this, but just because it's fairly basic. A shape is called convex. Anybody remember this word? I don't know if people learn about convex shapes when they're kids in high school. I don't know. It's not that complicated, but a shape is called convex when it's a little hard to say, but once you get the idea in your mind, it's very easy to understand what convex means. When the straight line connecting any 2 points in the shape lies entirely inside the shape. This is what it means to be convex. The straight line connecting any 2 points in the shape lies entirely inside the shape. I don't know if that sounds simple to you, but actually once you get the idea in your mind, this is fairly easy to just look at a shape and immediately decide if it's convex or not. For example, a square. A square is convex. Why is that? I'm saying the straight line between any 2 points in the shape lies entirely within the shape. So you have to imagine, what if I take 2 points inside the square? Is it true that the straight line connecting those 2 points lies entirely inside the square? Yes, it is true, all right? And that's not a special property of those 2 points that I chose, but any 2 points inside the square, the straight line connecting them is inside the square. All right, what about a triangle? That was it. How about, it doesn't have to be an equilateral triangle? I missed the dot. It's all right. Put the dot there. Is this convex? The answer is yes. If you take any 2 points inside the triangle and connect them with a straight line, that straight line still lies inside the triangle. It doesn't have to stretch out beyond the edges of the triangle. All right. What's an example of a shape which is not convex? Maybe something like, how about sort of a Pac-Man type shape? Y'all remember Pac-Man? Yeah. I know about Pac-Man. The Pac-Man is not convex, so this one is convex. This one is convex. Can anyone describe 2 points inside the Pac-Man so that the straight line connecting them reaches outside of the set? Yeah.
Over and under the mouth.
Yeah, over and under the mouth. Yeah, if you know something about Pac-Man, you know this is Pac-Man's mouth. He likes to eat things. And if you take a point up here and a point down here, then the straight line connecting them does not lie entirely inside the shape because it goes outside right there. So this is not convex. Did you hear? I heard this a few months ago. I didn't plan on talking about this, but there's currently a live-action Pac-Man movie in development. Can you believe it? That sounds like a bad idea to me. All right, this is what convex means. Typical like shapes which you encounter in real life usually are not convex. Like, you know, the shape of my hand. This is a picture of my hand. Is that convex or not? No, there are many ways that you can choose 2 points in the shape where the straight line connecting them is no longer in the shape. I could take that point and that point, say, and that straight line connecting them is not in the shape anymore. All right, how about like a shoe? This is what a shoe looks like, right? I don't know. Is that convex? No? Can you tell me, how do you find like 2 points on there? Yeah.
Like the heel of the shoe.
Uh-huh. Yeah, sort of over here and over here, right? It's not convex because of that little thing. One way that I think about it is like this shape kind of has if you don't mind my I'm not afraid to say stupid things if it gets the point across. This shape has like a little innie area, right? The thing that sort of sticks into it. That's not allowed for a convex. If you see any kind of innies, that's not okay for a convex. Although an outie is a little, I mean, does this count as an outie? That's okay to have a part that sticks out as long as there's no part sticking in, right? That's not okay for a convex set. So these things both are not convex. All right. Great. So typical real-world shapes which have like wiggly edges, like a triangle is convex. But if I have a triangle with some kind of slightly wobbly edge, now it's not convex anymore, right? And for that reason, like shapes which you find in nature, say, tend to not be convex. Biological type things are always sort of wiggly around the edges. Although maybe like, the sun, there are perfectly round shapes in nature. A circle is convex, but this one is convex. This is not convex, all right? I hope everybody's getting the idea here. Because of all those wiggly wobblies along the edge, you can find sort of points like, I need 2 points inside the set, which stretches, the line connecting them stretches outside. Can you even see that? Because of the innie right there. There's a little innie. All right? Let's talk about the convex hull. That's the real thing that we are aiming to talk about. Every shape has a convex hull. The convex hull is what you get if you sort of fill in all the innies. Any of these shapes that's not convex, you could fill in all the parts which make it non-convex, and then it becomes a convex shape. So the definition of this is it's the smallest shape which contains the original shape but is convex. The way you get this is called the convex hull. You start with some shape which may not be convex, and then you just fill in all the innie parts and make it into a convex shape. That's called the convex hull. So the convex hull is obtained by filling in portions of the original shape in order to make it convex. All right? So for example, with the Pac-Man by itself is not convex. What is the convex hull of the Pac-Man? It means you just fill in the innie. Yeah, can you say? She said it's a circle. Actually, this is a good answer, although not exactly correct. So it's not quite a circle. It is, maybe on my drawing it will be indistinguishable from a circle, but it's the shape that you get by filling this in by taking a straight line here. If you make it into a whole circle, that involves adding a little bit of extra stuff out here, which actually is not really necessary to make it convex. I'm going to try to add in only enough to fill in that innie part. And then, of course, we also take all the original shape too, all right? So the Pac-Man's convex hull, I'm going to try and redraw this. This one here, the convex hull is something which has a straight line there and then looks like a circle for the rest of it. That's the full shape that you get after filling in the non-convex part of it. All right? Or what about my my hand? How about that? What's the convex hull of that? It's what you get by filling in all the innie parts. So if I were just like scribbling on top of this, it would be, I connect, so I have a little innie region right there, and I'm going to fill that in by connecting a straight line from here to here, because that's what it takes to fill in that whole thing. And then you also fill in, between each of the other fingers, like this, like this, like this. Now this, my finger, do your fingers do this? My finger's a little wiggly in that way, and I have to fill that in too if I want to make it convex. Probably your drawing doesn't have that, but I got to fill that in too. All right. And then there's a weird little innie right there. Depending on the specifics of your drawing, you may have to fill in some extra little innie bits. Here I have this kind of thing. All right. But anyway, the convex hull is everything inside here now. All right. One thing you want to be careful about is, actually, I did not get enough here. I connected here and here to fill in the space between the two fingers, but actually there's still a innie here, which I sort of created a new one. You got to fill that in too. So really it should go straight across there also. If you drew this yourself, it probably didn't look the same as mine, so you might not have seen that kind of detail. All right, and actually there's an innie across the bottom too. Fill that in too. All right, this is the convex hull. Any questions about how we get that? It is always bigger, right? Convex hull is automatically bigger. Although if what you start with is convex, then the convex hull is just the same as what you started with. So the convex hull is always, can I say equal or bigger than the original shape? It involves adding more stuff. Although if what you start with is already convex, you don't have to add anything. So the convex hull is always equal or bigger to the original shape. Just to make sure everybody is with it, I have a fun handout of just a bunch of cute shapes, and your job is just to draw the convex hull of each one. You can just draw right on top of it the convex hull of the cute shapes. If it's already convex, then you don't have to change the shape. Convex hull is just the same shape again. If you know what you're doing, this will probably only take you a moment to do all of these. So draw in the convex hulls. I will walk around and make sure everybody's doing well. Everybody got one? What it involves typically will be sort of adding in some more straight lines and then shade in the inside. That's what I want to see.
Yeah, that's what you drew has some extra homogeneous to it. Just like you put a straight line there, you should also put a straight line.
When you're shading these in, technically you should be shading the entire thing, like on mine. The convex hull includes all the original stuff plus whatever you add in. So you should be scribbling in the whole thing. Those look great. There's actually a little more than that. All right. Mm-hmm. I don't care how artistically cute your pictures look. Mm-hmm. right, can we talk about these? Everybody is with it, I think. I meant to say this before. Maybe I should have said this before, but another way to think about this is the convex hull. Another way to think about how you get this, I said it's like what you get by filling in all the innies. If you look at your pictures, you will, I think, agree that this is another way to describe the same shape. The convex hull is the shape you get if you were to wrap a rubber band around the shape. It really is like that's what happens if you were to wrap a rubber band around your shape. It will enclose a slightly larger area, and that area that is enclosed by the rubber band is the convex hull. It should be the same if you're looking at your pictures. Think of it in those terms, and I hope that it is what it looks like. Okay, here is this. So what did you say? You should have said the heart, you got to fill in sort of the top part here. And then also there's a slightly non-convex part. Trying to make it bigger. Get bigger. Come on. All right, I'll just zoom in. There's also a part sort of down here that deserves to be filled in. But that's what the convex hull of the heart is. I filled in something on the top and also something on the lower right-hand side. This one, you got to fill in like this. This is like the rubber band, right? When it stretches around, it looks something like that. And then it's all the area inside there. There's no real tricks here. I think as I was walking around, pretty much everybody was doing well with these. So that's the convex hull of that one. The circle is already convex, so its convex hull is just the same as the original shape. All right. This house you have to add in there and there, and fill that in. This one you have to connect there and there with straight lines. What you are adding to the picture should always be made up of straight lines. The moon type thing needs a straight line there. And then this sort of happy worm. It wasn't originally a happy worm, but when I drew it, I like my pen slipped and I got the mouth, and then I decided to make it a little happy worm. Something like that. All right? That's the convex hull there. All right. I think, do you, I mean, after like 20 minutes of explanation, do you agree with me that this is kind of a simple idea? Like, once you get it in your mind, it's very easy to write down or draw the convex hull of something. All right? Okay, I would like to point out something that, like, what does this have to do with gerrymandering or weirdness of shapes? Something to note. If a shape is not so weird, I will say nice. By nice, I mean, I don't know, something vaguely like a polygon or a circle or something, even if it has a somewhat wobbly edge around it, something like, this maybe. This is sort of like a lumpy thing. But it's more or less a nice, compact-looking shape. All right. This thing, the convex hull, is not so different from the original shape, right? Like, what do you have to add into this to make it convex? Well, you have to. There's some little innies here and there, right? But they're fairly small, right? I mean, when you make the convex hull, I would have to add some area here, a little bit here, right? All of these like slight weirdness around the edges does not involve a lot of additional stuff when you go to the convex hull. So if a shape is nice, the convex hull is not so different from the original shape. But if the shape is a wormy kind of thing, like there's one on the paper that looks kind of like this, all right? The convex hull of that is really quite different, is much bigger in terms of area. The convex hull here of this is much bigger. Bigger, I mean in area. Because you have to add in all of this stuff and you have to add in all of that stuff, right? Which is big areas. Okay, so the moral of the story is the convex hull of a normal shape, the convex hull is pretty much the same as the original shape, but of a wormy shape, the convex hull is much bigger. We got 6 minutes. Let me just tell you the definition of the convex hull ratio. This is the specific measurement. The convex hull ratio. It's a ratio. What it is it's, I'm usually just going to write it as CH for convex hull. It is a fraction because it's a ratio. And what it is it's the area of the shape divided by the area of the convex hull. All right. This is called the convex hull ratio. You take the original area and you divide by the area of the convex hull. So when the shape is normal, I'll say when the shape is not so weird, then the area of the convex hull is only a little bit more than the area of the original shape. So when the shape is not so weird, I will say the numerator is a little bit smaller than the denominator, which means as a fraction, I'm talking about maybe something like 9 divided by 10 or something. The numerator is only a little bit smaller than the denominator. As a fraction, that is close to 1. 9 divided by 10 is 0.9, something like that. So, so the CH will be close to 1. All right? But when the shape is weird, super wormy, when the shape is weird, the denominator is much bigger. And so the convex hull ratio is close to 0. This would be like 1 divided by 10 or something. It's close to 0. All right? And this is that, that number. It can tell you, it has to do with measuring the areas, and it can tell you if the shape is weird or not. All right? I think that'll do for now. We'll do some real examples next time. Oh, I do have homework to hand out, just because it has some pictures about convex things, although you won't have to actually find the convex hull ratio, but there's some simple geometric things about convex sets.